Okay, let's begin. So the class is Introduction to Algebra for Math Competitions, and I'm your instructor, Shreyas Shrivastava. If you have any questions, please message me in the message box or email me at shreyasshrivastava@alphademic.org. Please keep your mic muted. After each topic, I'll present some questions to test your understanding and then discuss the solutions. For those who find the questions too easy, there will be some challenge questions in the end. Most importantly, have fun. I'll try my best to make the class fun and understandable, but I'm not perfect. So if you see any mistakes, feel free to point them out. And you can review the session at Alphademic's YouTube channel, which is right here. And please consider subscribing to them as well. So here are the topics for this week. First, we're going to look at functions. Then we're going to look at graphing functions. Then we're going to look at polynomials. And then we're going to go over some challenge questions. This lesson was prepared with the help of the Introduction to Algebra book from AOPS. Functions. So basically, a function is like an equation essentially where every x has one y output. So the domain of the function consists of all the possible y's that can be put into the function. You can think of a function as like a machine or something. So like if you input, if you input like an x, you can only get one possible y. But if you cannot get like two y's, so you can't get like y1 and y2. That's not possible. That's not gonna be a function then. That's basically what a function is. So a function, like the domain is all the possible x's that you could put into the function, and the range is all the possible y's that can be outputted from the function for every x. So for example, if you want to find the domain and range of the function 2x squared minus 5, you can confirm that this is a function because for whatever x you put, you can only get one y, which is true. If I put 1, I can only get -3 out of it. So the x's that satisfy the function are all the real numbers, because if it's imaginary, you're not allowed to put it in. And then, so it's just all the real numbers. And then by the trivial inequality that x squared is always greater than or equal to 0. So the range is y is greater than or equal to -5. Combining functions. So you can apply the basic operations to functions as well. So if p of x is equal to 2x and q of x is equal to 3x, p of x plus q of x is equal to 2x plus 3x or 5x. P of x minus q of x is going to be equal to 2x minus 3x or -x. P of x times q of x, that'll be equal to 2x times 3x, which is just 6x squared. And then p of x divided by q of x is going to be equal to 2x over 3x, which is 2/3. So you can use your basic operations for functions as well. And composition is when you take the output of a function as the input of another function. This symbol right here, it's like a circle, can be used for composition functions. So if you see if there's like two functions, say f of x and g of x, like f of x and g of x, and if you see this symbol right here, f circle g, that tells you that you're combining essentially the functions, and it becomes f of g of x. That's how you say it, f of g of x. So that's composition of functions. I'll show you an example. Yeah, so here's an example composition function problem. So if it says let f of x be equal to 2x minus 6 and g of x be equal to 3x minus 9, find f of g of 2. Or I could have also said like kind of like this, I guess. So like this, f of g, where the 2, so it's like 2 like that. So you're trying to find f of g of 2. So first what you do is you evaluate g of 2. So g of 2 will be 3 times 2 minus 9, which is -3. So now that you have g of 2 is equal to -3, so this is -3, you want to find f of -3. And f of -3 will be -3 times 2 minus 6, which is -12. So our answer for what is f of g of 2, that's going to be -12. So that's basically what composition of functions is. Inverse functions. So the inverse of some function f is written as f to the power -1, or like, so it's like f, and then the inverse function is written as this. This is how you write the inverse function. That's the inverse function. So if f and g are two inverse functions, if f of 2 is equal to 6, then g of 6 is equal to 2. So basically, if there's two inverses, like two functions that are inverses of each other, if I input some x and I get y out of this, so if f of x is equal to y, if I input the y into g, so if I put g of y, it'll be equal to x. That's basically what an inverse is. Or you can also write that as f of g of x is going to be equal to x. That makes sense, because if g of x is equal to y, right? If g of x is equal to y, and since f and g are inverses, then f of y is going to be equal to x. So that's basically what two inverse functions are. So if f of g of x is equal to x and g of f of x is also equal to x, then f and g are inverses. So here's an example using inverse functions. So the function f is the inverse of the function g of x is equal to 2x minus 3 over x plus 5. Find f of 4. So first you want to find what exactly is f of x. And since it's an inverse, you can say g of f of x is equal to x. We saw this previously. So since g of f of x is equal to x, and you know that g of x is equal to 2x minus 3 over x plus 5, you can also write this as 2 times f of x minus 3 divided by f of x plus 5 is equal to x. You can cross multiply. You multiply f of x plus 5 to both sides. You're going to get x times f of x plus 5x is equal to 2 f of x minus 3. And if you like subtract x f of x from both sides and you add 3 to both sides, you're going to get 5x plus 3 is equal to 2 minus x times f of x. So now we know f of x is equal to 5x plus 3 over 2 minus x. So now it's pretty straightforward. We want to find what is f of 4. Just plug 4 into here, you're going to get negative 11.5. Okay, so here's some problems. I'll give you guys 2 minutes to work on them. So the first problem says a function f is defined for all positive integers has the property that f of m plus f of n is equal to f of mn for any positive integers m comma n. If f of 2 is equal to 7 and f of 3 is equal to 10, then calculate f of 12. And this was from Mandelbrot. This competition was discontinued. So this problem is pretty easy. All you do is you want to find out f of 12. So you think f of 12, you want this to say mn to be 12. So like what two numbers could you put here? The first one I would think of is like 6 and 2. You could do 4 and 3, but that's going to be it's going to be the same thing basically. So if you do 6 and 2 here, you want to find out, you already know f of 2 is equal to 7. So you want to find out what is f of 6. And we're given f of 2 is equal to 7 and f of 3 is equal to 10. So you can do f of 2 plus f of 3 is going to be equal to f of 6, because that's basically what the function states. F of m plus f of n is equal to f of mn. And we know this is 7, this is 10, so f of 6 is 17. So that's going to be equal to 17. So now that we know f of 6 is equal to 17, and you know f of 2 is equal to 7, you can sum those two. 7. And if you do f of 6 plus f of 2 by this function, you're going to get f of 6 plus f of 2 is equal to f of 12. And that's going to be 24. So our answer is 24. That was a pretty straightforward Mandelbrot problem. You just have to identify like what you're going to do, like what two numbers are you going to multiply to get to 12. That's basically all it was. Okay, this is a math cons problem. So it says let m n equal to m over n plus n over m for all integers m comma n not equal to 0. What is 5 number 8? It's from math counts, this symbol. So you just plug 5 and 8 into this. If m is equal to 5, 8 is equal to n, then you're going to get 5 over 8 plus 8 over 5. That's basically all your answers. It's just going to be equal to 40. So 40 plus 25 plus 64, which is going to be 89. So it's 89 over 40. That was also a pretty easy question. Okay. Let f of x be equal to 3x minus 8 and g of f of x be equal to 2x squared plus 5x minus 3. Find g of negative 5. All right, so this one you had to think about a little bit more. So you want to get g of negative 5 in the end. And you're given, you know what g of f of x is, the function for that. So what you want to do is you want to find out when is f of x equal to negative 5. You want to find the x such that f of x is equal to negative 5. And that's the x you're going to input into this function. So f of x is equal to negative 5 means 3x minus 8 is equal to negative 5, or x is equal to 1. So we want to find out what is g of f of 1. Because f of 1 is equal to negative 5, that's the same thing as this. So when you input x is equal to 1 into this, you're going to get 2 plus 5 minus 3. So our answer is 4. So that one you had to think about a little bit more. But it's pretty simple, these questions especially. Okay, graphing functions. So this is going to be a little bit more difficult than the previous lesson we were talking about. So graphing functions is similar to graphing the function graphs we mentioned in previous lessons. Just remember, in a function, every x has only one y. That's really important to remember for functions. To see if a graph is a function, you can use the vertical line test. If the vertical line intersects the graph at more than one point, the graph is not a function. I'll show you why. So like, I'm just going to take a random graph. Let's just say we take a circle, right? If the vertical line So the vertical line hits it at 2 points. Let's just say this is some point x comma y, and this is some point x comma negative y. It's not going to be a function because the rule for a function is every x has exactly one y, but this has two y's. And the reason this is true is because if you write x squared plus y squared is equal to k squared, for any given y can be like the square. Let's just say like x is equal to 0, y can be both positive k and negative k. So that's kind of why a circle is not a function, because every x actually has two y's. Okay, so here's an example. Graph the function 1 over x. So for this one, what you do is you want to look at like the end bounds. So for example, like let's just say x is equal to like a big number, like 1 million or something. Clearly, x is going to tend towards like 0, right? So as x approaches infinity, it's going to go towards like 0. So as the numbers get bigger, it's going to keep on approaching 0. And as the numbers become more and more like close to 0, like 0.01 or something, the numbers are going to go up. So it's going to be something like this on this side. Wait. Something like this. It's not going to actually cross the x-axis ever. And then that's for the positive x's. And if it's a negative x, as x approaches 0 again, it's going to go towards negative infinity. So it's going to be something like this. And then it's as you get like more negative numbers, it's going to approach 0 again. So that's a graph of 1 over x. It's something like this. It's like that and then that. Transformations. Transformations for functions are similar to the ones that we talked about like last week with quadratics and stuff. So for function is y is equal to f of x plus k, then y is equal to f of x is shifted up k units, which kind of makes sense because every y is going to have a value k more than if it wasn't plus k. And if k is negative, it's going to be shifted down k units. And if y is equal to f of x plus k, then the graph is shifted k units to the left, which also makes sense. And then if k is negative, then it's going to be shifted k units to the right. If there's a coefficient behind the f of x, so like if it's like 5 f of x or something, that's what I meant by that. Then the function either stretches or compresses. So, or if the coefficient is negative, then you're basically going to flip the function. So you're sometimes going to flip it. So if it's like this, you might just flip it like that. And if your coefficient's like less than 1 typically, like if you're dividing by a number, then it's going to become more compressed. And if it's like if it's like greater than 1, then it becomes more stretched out. If you put a coefficient inside the function itself, or if you write it as f of k of x, like f of kx is equal to y, then the function gets stretched horizontally by a factor of k. Yeah, so like if it's in behind the function itself, like 5 f of x, it's going to be a vertical stretch. And this, if it's f of kx, then it's going to be a horizontal stretch. So by that I mean like it's going to be like if it's like this normally, if it's vertical stretch, it's going to be something like that. And then it's also possible it goes more like that. That's kind of what I mean by the horizontal vertical stretch. Using the graph of y is equal to x squared, graph y is equal to x minus 3 whole squared plus 4. So first you want to graph y is equal to x squared. We kind of talked about this last week. It's going to be something like that. That's y is equal to x squared. So now you think about it this way. If it's x minus 3 squared plus 4, you're going to shift it 3 to the right because it's x minus k, which is k units to the right. So this is going to go here. So it's going to be like this. And since it's plus 4, it's going to be shifted 4 up. So this is going to be your function. So it's the exact same thing. Since there's no coefficient, it's not going to be stretched or compressed. So that was pretty easy. Okay, inverse functions. Something important to know is if two functions are inverses, we talked about this, then if x comma y lies on one of the inverses, then y comma x lies on the other. Because since if f of x is equal to y, and f of x and g of x are inverses, then g of y is equal to x. So some of you guys might have seen this, but if you have like the two functions, since x comma y lies on one of them and y comma x lies on the other, this is simply the definition of an inverse function. And then this is also a reflection over the line x is equal to y. So that's something really important to notice, is that if two functions are inverses, they're simply the reflections of each other across the line y is equal to x. And if a function has an inverse, then there cannot exist a horizontal line that intersects the function at more than one point, because the inverse wouldn't be a function then. I'll show you why. So like, take this function for example. It intersects at 2 points, right? So let this point be like negative x, let's just say like negative x comma y, and then this point's like a comma y. Then when you take the inverse of this function, then that's going to tell you like g of y should be equal to also one value, right? But g of y could be equal to a, or it could be equal to negative x. So that's kind of why it cannot, the horizontal line test proves for inverse functions. All right, here's some problems. I'll give you guys 4 minutes to work on them. Okay, let's begin. So the first question says, if 2 comma 3 lies on y is equal to f of x, find a point that must be on the graph y is equal to f of 2x plus 3. So we know f of 2 is equal to 3. That's basically all we're given. So since all we know is f of 2 is equal to 3, we can set 2x plus 3 equal to 2. And we're gonna get x is equal to negative half. So the reason I did this is because if I plug negative half into this, I'm going to get 2 times negative half, which is negative 1, plus 3, which is 2. So f of 2, which we already know is 3. So we get 3 minus 5 is the y coordinate. So 3 minus 5 is negative 2. So the point that must be on the graph f of 2x plus 3 minus 5 is negative half, comma, negative 2. So that's our point. Okay, so this one's pretty hard, but if you just notice one small thing, it'll help you a lot. So I talked about the graph f of x is equal to 1 over x before. It kind of goes like this, and then like this, something like that. So that's kind of the general form of the graph. That's f of x is equal to 1 over x. So if you notice, if f of x is equal to 1 over x, f of x plus 3, let's just write the g as g of x. I'll just graph that to avoid confusion. So then f of x plus 3 is going to be equal to 1 over x plus 3. So that's something really important to notice. So once you realize that if you can write it like this, then all you need to notice is that we talked about how if f of x is your base function and you do f of x plus k, you shift your function k units to the left is k left. So if we're shifting f of x k 3 units to the left, 1 over x plus 3 is just going to be the graph of 1 over x, but 3 units to the left. So normally it would be like this. Instead, it's going to be something like this, kind of like that. And then normally this would be like this, but now it's going to be like this. So your graph's going to consist of this on this side, and then this on the in the negative side. So that was something really important you had to notice. That you can write the function as in terms of another function. In this case, it was in terms of 1 over x. Okay, graph y is equal to x cubed. So first you want to determine the middle point, which in this case would be 0, 0. We already know this point for sure. So as you go towards like infinity, for example, so what I like to do is I like to like look at the higher numbers to see in general where is the function going. So like if this is a really large number, then this x cubed is also going to be a really large number. So as you go towards infinity, it's gonna go like that. And then as if x is negative, then x cubed is also negative. So as you approach negative infinity, it's gonna go towards a negative infinity. So it's gonna be like this. So that's your graph y is equal to x cubed. As you go towards infinity, it goes towards positive infinity. And as you approach negative infinity, it goes towards negative infinity. When you graph you typically for these type graphs, you want to look at the ending bounds. Like you want to see as you're going towards infinity, what's going to happen, or as you go towards the negative infinity, what's going to happen. That kind of helps you like generalize what the shape's going to be. Polynomials. A polynomial of one variable is a sum of terms where each term is a constant times the variable raised to a non-negative integer power. So this is an example of polynomial, x squared plus x plus 1. This is another example, 2x to the power 5 plus 3x cubed plus 4. And the leading terms of a polynomial is the term with the highest power, which will be like, in this case, it's going to be x squared, since 2 is higher than all these other powers. And then in this case, it's going to be 2x to the power 5, because it has the highest power again. The degree of a polynomial is the power of the leading term. So the degree of this polynomial is going to be 2, because the highest power term is x squared, and that has degree 2. And same thing with this one. It's going to, this one's going to be 5, but use a similar technique. So you look at 2x to the power 5, and you notice the power is 5. Coefficients are the constants that are multiplied to each term. So the coefficient of like x squared is 1, because x squared is also 1 times x squared. The coefficient of 2x to the power 5 is 2. The coefficient of 3x cubed is 3, and so on like that. The leading coefficient is the coefficient of the leading term in the polynomial. So in this case, the leading coefficient is going to be 1, because x squared is the leading term. And in this case, the leading coefficient is going to be 2, because 2x to the power 5 is the leading term. If the leading coefficient is 1, the polynomial is said to be monic. So this polynomial right here is monic because x squared, the leading term, has a coefficient of 1, but this polynomial is not monic. When you write a polynomial, you write it with the terms with higher powers decreasing, like the powers decrease from left to right. And the constant term is the term that has a numerical value with no variable with it. So in this case, 4 is the constant term and 1 is the constant term. Something else is like the general form of a polynomial is something like this. This is kind of how you write a polynomial. So you start with the highest power and some coefficient and so on. So in the polynomial in the previous example, so like it said like 2x to the power 5 plus 3x cubed. So you might wonder, well, I wrote x to the power n and then x to the power n minus 1. Then what happened to x to the power 4? Why is there no term? That's simply because there's no coefficient in that case. Like the coefficient 0, sorry. So that means that a2 is equal to 0. So that's why there's no x to the power 4 term. So that's kind of how you write your polynomial. I'll just write one more time. So you write from left to right, the powers go down, and there's going to be, typically, there's going to be like n terms, but some of the terms might be 0 if the coefficients are equal to 0. Addition and subtraction of polynomials. So addition and subtraction of polynomials is pretty straightforward. Just remember, if you add two terms with equal power, you sum the coefficients of the two terms, and if subtraction, you subtract the coefficients of the two terms. It's pretty similar to the techniques we talked about before with like summing quadratics and simple linear equations, stuff like that. So here's an example. It says if f of x is equal to x cubed, I think this should say plus 4x. So if f of x is equal to x cubed plus 4x plus 7, and g of x is equal to negative 3x cubed plus 2x squared plus x minus 7, find f of x plus g of x and f of x minus g of x. So if we sum the two terms, first let's look at this one. So we sum the two terms, you're going to get x cubed plus 4x plus 7 plus negative 3x cubed, so just minus 3x cubed, plus 2x squared, plus x minus and minus 7. So if you sum the two terms, if you sum these two terms, the two functions, it's going to be you take the coefficients and you add them. So the x cubed plus negative 3x cubed, that's going to become negative 2x cubed. And then you notice there's a 4x here and an x here. So if you sum them, it's going to become 5x. It's pretty straightforward. And then you have 7 here and minus 7, so those cancel out. And then you have just a 2x squared here. So that's going to be what you get. That's what you're going to get if you do f of x plus g of x. And if I was to write this as a polynomial, this would actually, this is acceptable, but the better way to write it is the 2x squared term right after the negative 2x cubed, because the power should decrease as you go from left to right. Again, you don't have to do that, but it just looks better if you do that. And people will probably understand it much better. Okay, and if you do f of x minus g of x, you're just going to do x cubed plus 4x plus 7 minus this whole thing. So that's just going to become 4x cubed minus 2x squared plus 3x and then plus 14. So it's pretty straightforward. Just remember, if they have similar powers, you have to do the coefficient thing where you add the coefficients and then you place the term like that. Multiplication. When you multiply two polynomials, remember the distributive property. Since the number of terms in any polynomial can be really high, you have to make sure not to miss any cases when doing the distributive property. So here's an example. Expand 3y squared minus 2y plus 3 times y cubed minus 2y squared plus y minus 7. So we use the distributive property. You're going to get 3y to the power 5 minus 6y to the power 4 plus 3y cubed. Pretty straightforward. Minus 21y squared. And then minus 2. And then we're going to take the negative 2y term and do the distributive property. So you're going to get negative 2y to the 4th plus 4y cubed minus 2y squared and then plus 14y. And then you can use the 3 and do the distributive property, and you're going to get plus 3y cubed minus 6y squared plus 3y minus 21. So you can see there's a lot of terms here. I'm not going to group them all together right now, but like you can see there's a lot of terms. You have to be very careful when you do the multiplication, because missing out on even one term ruins your whole answer. Here's some practice problems. I'll give you guys 1 minute, 2 minutes to work on them. Okay, let's discuss them. First problem is if p of x is equal to 2x minus 5, q of x is equal to 3x squared plus 7x minus 4, find p of x plus q of x. You can simply sum the terms, so it's going to become 3x squared and then plus 9x minus 9. I don't think I need to explain how I got this, but it's pretty simple to understand. Just sum the like terms, combine the coefficients in the case if they're like terms, have similar powers. Okay, if p of x is equal to 2x minus 5 and q of x is equal to 3x squared plus 7x minus 4, find p of x times q of x. We use the distributive property, so it's going to become 6x cubed if you don't know the distributive property, I think I talked about it, I think 3 weeks ago or something. So you can look at the past videos. And then you can just sum the like terms. So you're going to get 6x cubed minus x squared minus 43x plus 20. Again, pretty simple. Nothing too hard here. Let f of x be equal to x to the fourth minus 2x cubed plus ax squared plus x plus 3, where a is a constant. And if f of 3 is equal to 2, find a. So you plug 3 into this function, you're going to get 81 minus 54 plus 9a plus 6 is equal to 2. This is just all plugging stuff in this case. So it's going to be 27 plus, so like 33 plus 9a is equal to 2. And now that you know 33 plus 9a is equal to 2, you can solve for that. So negative 31 over 9 is a. Okay, here's some challenge problems. How much time do we have? I'll give you guys like 1 minute, 2 minutes to work on them, because I'm kind of going over time now. Okay, let's discuss them. So the first one says, how many square units are in the area of the triangle whose vertices are the x and y intercepts of the curve y is equal to x minus 3 squared times x plus 2. So we talked about x and y intercepts, I think, last week. So x-intercepts are when y is equal to 0, and y-intercepts are when x is equal to 0. So first, let's find the x-intercepts or y is equal to 0. So when y is equal to 0, right, x minus 3 squared times x plus 2 should be equal to 0. This happens when x is equal to 3, so 3 comma 0, and also when x is equal to negative 2. And the y-intercepts are when x is equal to 0, so 0 comma some y. And when x is equal to 0, you get negative 3 squared times 2. So that's going to be 18. So if I graph them now, if you could do this fast, you probably, in math counts, I want to recommend graphing them actually, because it's pretty easy to notice that this is your standard triangle where the base is, okay, so your base is clearly of length 5, because 3 comma 0 to negative 2 comma 0 is 5, and your altitude is going to be 18, because this is 0 and it goes up to 18. So I know this is not a geometry class, but the area of a triangle is the base times the height divided by 2, and that's going to be 45, because 5 times 18 divided by 2 is 45. So your answer is 45. But in math cons, I wouldn't actually recommend graphing them. I would simply notice that they're on the same line, these 2 points. So the base is 5 and the altitude is 18. Graphing them wastes too much time in math cons. Okay. Let f be a function satisfying f of xy is equal to f of x divided by y for all positive real numbers x and y. If f of 500 is equal to 3, what is the value of f of 600? This is an AMC 12 problem. It's actually pretty easy for an AMC 12 problem. So basically, you notice that let y be equal to 1.2 times 1.2. So like that. And this is equal to f of 500 divided by 1.2. This is simply what the function states. F of xy is equal to f of x divided by y. So if x is equal to 500, y is equal to 1.2, then you have f of 600 is equal to f of 500 divided by 1.2, or 6 over 5, same thing. So f of 500 is equal to 3, so this is 3. So it's the f of 600 is going to be equal to 3 divided by 6 over 5, which is 15 over 6, or 5 over 2. So we're done. Or 2.5, any of those. Okay, last problem. For what constant k must f of k always equal the sum of the coefficients of f of x for any polynomial x? I put this problem as a challenge problem because I've seen this type problem in many math competitions where they're asking you find the sum of the coefficients of a polynomial or something, but it's pretty easy. It's nothing like that hard. I'm just going to write the polynomial out first. So this is your polynomial. We talked about the standard for a polynomial before. Something like this. So this is your polynomial. So you want the sum of your coefficients, so you want an plus an minus 1 plus an minus 2 all the way to plus k. So all you have to do is just plug x is equal to 1 into this. If you plug x is equal to 1 into all of this, this becomes 1, this becomes 1, everything becomes 1. So it's just going to become a of n plus a of n minus 1 plus a of n minus 2 all the way to k. So if a question asks you, they give you a polynomial or something, like some really weird polynomial, and they say, what is the sum of all the coefficients of f of x? Just plug 1 into the equation. It's that easy. You just put f of 1, and that's the sum of your coefficients. It's pretty straightforward. And I've seen this type problem pop up a lot on math competitions. All right, thank you for watching. This was the second to last class, so next week's going to be the last class. So we're gonna pretty much finish the whole intro to algebra book by the end of next week. And so please consider checking the YouTube channel out of Alphademic's YouTube channel to review the session again. Okay, thank you.